Achieving perfect operational anonymity on the internet requires a highly disciplined approach to standard web infrastructure. The baseline for this configuration involves deploying a purely static architecture containing only HTML and CSS files onto a content delivery network, or CDN. A CDN is a geographically distributed group of servers that cache static assets closer to users to accelerate load times. Crucially, this high-privacy deployment utilizes the provider's default subdomain rather than a custom web address. Relying on this default subdomain bypasses the global domain registrar system. This neutralizes the traditional WHOIS public association leak. WHOIS is a public database containing the contact and registration details of domain name owners. Next, the administrator must fund the CDN account using prepaid cryptocurrency. This effectively severs the financial KYC paper trail. KYC, or Know Your Customer, is a financial regulatory requirement that mandates businesses to verify the real-world identity of their clients. This animated diagram shows the required operational topology. The administrator must mask their origin IP address from the CDN's access logs. A virtual private network, or VPN, is a service that creates an encrypted connection from a device to a remote server. By using a VPN, the initial asset upload is routed through a remote node, keeping the administrator's actual physical location completely off the record. By isolating the files in a static storage zone, the administrator eliminates the need for an origin server, databases, or execution environments like PHP. This effectively shrinks the server-side attack surface to zero. This stacked configuration flawlessly hides the administrator's identity from external observers. However, operational anonymity does not equal system resilience. There is a critical distinction in threat modeling between hiding the identity of the host and protecting the hosted data from censorship. A CDN provider operates as a centralized intermediary. As a legitimate business, they're governed by local jurisdictions and maintain compliance teams subject to copyright takedowns and local laws. In this animated diagram, we zoom in on the storage zone. Despite having no knowledge of the administrator's real identity, the CDN provider retains physical possession of the raw, unencrypted HTML files. A simple legal request can trigger an administrative kill switch. Because the centralized provider possesses this authority, they require zero forensic de-anonymization to terminate the content. Once the zone is wiped, the edge servers instantly drop their cache data. Centralized infrastructure prioritizes platform longevity and legal compliance over the operational security of an individual account. If centralized intermediaries inherently possess a kill switch, true censorship resistance requires mathematically eliminating the middleman. To eliminate the middleman, operators often look towards decentralized Web3 architectures, utilizing blockchain-based domains and IPFS data pinning. IPFS, or the Interplanetary File System, is a peer-to-peer network protocol that distributes data across thousands of independent nodes rather than a central server. The user experience of this model is highly appealing. It offers human-readable web addresses and a distributed storage mesh that lacks a single point of failure. This architecture collapses under high-risk hosting conditions due to the anonymity versus incentivization paradox. To guarantee data remains online in an IPFS network, operators financially incentivize nodes to pin files, recording the transactions on a public blockchain ledger. This creates a permanent metadata trail. Traffic analysis firms trace these records backward to map the exact physical infrastructure hosting the illicit data. A secondary architectural chokepoint exists in the resolution layer. Browsing domains like .crypto or .zil over the standard internet requires an intermediate centralized gateway server. Querying these gateways forces the user to hand over their origin IP address and their exact search intent to a single, easily monitored server. By combining centralized resolution gateways with public financial ledgers, incentivized Web3 networks function as massive forensic honeypots. High-risk operators actively reject the Web3 model in favor of the established, battle-tested architecture of the Tor network. Tor's security relies on altruistic, volunteer nodes rather than market-based incentivization. An encrypted packet moves through a 3-node circuit without generating transaction records. Data is strictly routed, never persistently stored. When the connection closes, the system instantly dissolves the packet path, leaving no static target. This architecture exacts a severe toll on user experience. Tor enforces massive friction through high-latency connections and complex 56-character .onion addresses that are impossible to memorize. In this generated video, we visualize the effect of that friction. For operators evading active surveillance, a high-friction environment is tactically superior. Tor's heavy latency breaks automated mass surveillance web scraping. This forces adversaries to abandon algorithmic monitoring and engage in highly expensive manual human intelligence operations. In high-stakes threat modeling, operators gladly trade speed and human-readable interfaces for the mathematical deniability of a ledgerless, ephemeral network. Network engineers face a final architectural challenge: designing a system that achieves Tor's censorship resistance alongside Web3's human-readable usability, entirely without centralized gateways. This animated diagram maps the standard ClearNet resolution pathway. The foundational bottleneck of the modern Internet is the top-down nature of standard DNS resolution and the operating system network stack. DNS, or the domain name system, translates human-readable web addresses into numeric IPs, governed by central authorities and local Internet service providers. An alternative approach bypasses this stack using an application-specific overlay network, or ASON, deployed entirely through a client-side browser extension. In this animated diagram, we see the air-gapped browser navigating the new overlay network using purely local client-side resolution. The browser requests encrypted data shards directly from lateral peers. The web page interface is reassembled locally without ever touching a centralized Web3 gateway server. This architecture avoids the Web3 honeypot trap by relying on the altruistic, non-incentivized data sharding methods seen in networks like Freenet or I2P. This topology removes every traditional choke point: no central origin server to raid, no public ledger to audit, and no DNS registrar to subpoena. To execute a successful takedown of hosted data, law enforcement would have to simultaneously locate and destroy every individual volunteer node globally. Maintaining a stable, large-scale user base for a purely altruistic mesh remains incredibly difficult, cementing this architecture as the strict hard mode of network engineering. Pulling the network resolution layer entirely into a client-side sandbox bypasses the gatekeepers entirely. It realizes the theoretical limit of a sovereign, unstoppable web.